In this video, I'm going to introduce you to binomial expansions. To access the full lesson on this topic, visit parkermaths.com/y1 binomial. So we're going to begin by looking at Pascal's triangle. This might be something you've seen before, but don't worry if not, it's really easy to understand how it works. So we're going to start with a row of zeros with a 1 in the middle. And we're going to call that row 0. And then to get the next row, row 1, we take two consecutive values from row 0, say the 0 and the 1, and we add them together, giving us 1. We can then take the next two consecutive values, again 1 and 0, add those together, it gives us 1. We could continue along the length of this row in either direction, but we'd just be doing 0 plus 0, so there's no real point in doing that. Next up, we'll look at row 2. Imagine row 1 still has a row of zeros going along. I'll just put one either side. We would do 0 plus 1, which gives us 1. We'd have 1 plus 1, which gives us 2, and 1 plus 0, which gives us 1. We can continue this pattern for as long as we want. Row 3 would be 0 plus 1, which is 1. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 0 is 1. And then continuing on the pattern, we get row 4 being 1, 4, 6, 4, 1. And then we'll just do row 5 as well, which would be 1, 5, 10, 10, 5, 1. And you could continue that indefinitely. A key point that I'd just like to stress again though before we move on is that the first row we're actually calling row 0. And the reason for that is that later on when we look at calculating rows that are much further down in the triangle, it makes those calculations much simpler to do. Okay, suppose we start at the top of the triangle where there is a 1. And I want to follow a path along these numbers and get to another value in the triangle. Let's say we go on row 5, we want to get to the value 5. And suppose we're allowed to go left or right, but each time we go left or right, we have to go down one row. So there are several different paths that I could use to get down to this value here. If we look at those systematically, we could start at 1 and we could go left, 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 right. And I could write this as follows. A second way could be left, 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 right, left. And I could write this like so. And then we could do another way where we go left, left, right, left, left. We could also go left, right, left, left, left. And we could do right, left, left, left. And these are the only 5 possibilities that would allow us to get to 5 here. Because if we went right twice, we wouldn't have enough lefts to get us over to 5 here. And the key thing I want you to notice is that there were 5 ways of doing this, and the number here is 5. And feel free to check for yourself. But to get from the top to any other value in the triangle, this value will tell you how many different ways there are of doing it. For example, in this bottom left corner, this 1 here, there's only one way of getting there. I would go left, 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 left. The 10 here, there are 10 different ways I could get there starting at 1. Now, Pascal's triangle has lots of other interesting features which I'm not going to explore in this video because they're not related to the topic that we're doing. But if you're interested in finding out more about Pascal's triangle, I've put a link to a number file video in the extras section for this lesson. Okay, let's now take a look at what we mean by a binomial. So a binomial is a polynomial that is the sum of 2 terms. So let me just put some expressions on the screen. You might like to pause the video and see if you can identify which of these expressions are polynomials first of all. Okay, the polynomials are the ones inside the green box. Polynomial is an expression made up of the sum of terms which are powers of x, where the power is a non-negative whole number. So 0, 1, 2, 3, 4 and so on, you're allowed for powers. You can have different letters in there, you can have x's and y's. What you can't have are fractional powers or negative powers or things that cannot be written as the sum of powers of x. So we can't have this one here because it's got x to the power of a half, and we can't have this one over here either. Next, see if you can identify which of these are binomials based on the definition above. The answer is these two. We know that they're polynomials, and each one is the sum of two terms. So the purpose of this unit is to be able to take a binomial, put it in a bracket and raise it to a power, say 7, and be able to expand this without having to go to the trouble of writing out lots of brackets and expanding it the long way. Okay, so we're going to examine what happens when we expand some binomials to a power. Follow along with me for the first 3, and then after that, I'll get you started on the 4th one, and you might find that you can do the 4th and 5th ones for yourself. And then when we've got answers for all 5 of these, we'll take a look and see if we can spot any patterns that might be useful when doing binomial expansions. So to begin with, we've got 1 plus x to the power of 0, and anything to the power of 0 is just 1. Then we have 1 plus x to the power of 1. While putting something to the power of 1 is just going to leave us with the same thing as we started with. And so we just end up with 1 plus x. But I'm going to write it as 1 plus 1x. And the reason I leave those 1's in might become more apparent later when we've done the expansions and we're looking for connections. For 1 plus x squared, I could expand this using the shortcut, but what I'm going to do instead is do it the long way so that we can make some connections later on. So we've got 1 plus x, and if we square something, we're multiplying it by itself, so we can write it as 1 plus x multiplied by 1 plus x. And so when we're expanding any pair of brackets, we take the first term in the first bracket and multiply it by all the terms in the second bracket. That gives us 1 plus x. And then we take the next term in the first bracket and multiply that by everything. So in this case, that gives me plus x squared. And we can see that there's a simplification here. We leave the 1, x plus x becomes 2x. And then we leave the x squared on the end. But like in the last example, I'm going to put a 1 in there to make it 1x squared. Let me just get you started with 1 plus x cubed so that you set it out in a specific way. To get 1 plus x cubed, one way of doing it is to start with 1 plus x and then multiply it by 1 plus x squared. But rather than writing 1 plus x squared, I'll put what I found it was here. So 1 plus 2x plus x squared. Okay, so feel free to pause the video and expand this out, see what you get, and then do the same thing for 1 plus x to the 4. And then you could come back and check your answers with mine. So for 1 plus x cubed, we're going to take the 1 and multiply it by everything in the next bracket. And then we're going to take the second term x and multiply that by everything in the second bracket. Then we can simplify. We've got 1, and then 2x plus x gives me 3x. X squared plus 2x squared gives me 3x squared. And then we've got plus x cubed. But once again, I'm going to write this as 1x cubed. For the last one, we'll first write it as 1 plus x multiplied by what we got for 1 plus x cubed. Then we'll multiply out. We'll do 1 times everything in the second bracket. And then we'll do x times everything in the second bracket. Simplifying this gives us 1. And we've got 3x plus x, which gives us 4x. We've got 3x squared plus another 3x squared, gives us 6x squared. Then we've got x cubed multiplied by 3x cubed, so that's 4x cubed. And then we've got one lot of x to the 4. And there we go. So what I'd like to do now is look at the coefficients in each one of these expansions and see if you notice anything familiar. Hopefully you notice that the coefficients in each expansion form one of the rows of Pascal's triangle. And that's really useful because it means that whenever we want to do a binomial expansion, we don't have to expand out the long way. We can simply use the appropriate row of Pascal's triangle to find the coefficients. And because we labelled the first row as row 0, you'll notice that when we do something like 1 plus x to the 4, it's going to be the fourth row. 0, 1, 2, 3, 4. And so by having a row 0 instead of starting at row 1, it means the powers match up with the row that we're talking about in Pascal's triangle. Before we finish, let's take a quick look at why these coefficients are rows in Pascal's triangle. So let's take, for example, 1 plus x squared. The constant term is a 1, and that's because there is only one way of getting a constant in this expansion if you do 1 times 1. We also only have one lot of x squared, because here there's only one way to get x times x. But in the middle, to get 2x, there are two ways to get a term involving just x. We can do x multiplied by 1, and then we've got another term, 1 multiplied by x. And so we get a 2 because there are two combinations that gives a term involving x. Then we expanded 1 plus x cubed. Once again, there's only one way of getting a constant with the 1 times 1, and there's only one way of getting the cubic term using x squared times x. But when we consider the other terms, for example, the 3x here, we get that by doing x times 1 and 1 times 2x. But here, where we have 2x, remember in the last part of this question, we got that from x plus x, so that really could be written as x plus x. So really here, rather than just doing two parts of an expansion, there are actually three combinations that will give us a term involving x this time. We had the 1 times x, and instead of doing 1 times 2x, we could do 1 times x and then another 1 times x. So each of these values in this expression tells me how many combinations there are when I expand this bracket out of multiplying to get x or x squared and so on. And so it might be a bit complicated to work it out to get 6x squared. But what you would find if you'd not simplified any of these terms is that at some point you would have done x multiplied by x in a combination of 6 different ways. And that's why you end up with the 6 here. Now, to do these binomial expansions, it's not particularly important to be able to understand the details of why we use Pascal's triangle. But the key thing to take away from this video at the moment is that the coefficients of your binomial expansion will be one of the rows in Pascal's triangle.